Just like a short introduction, my name is Carsten. I'm an AI consultant and data scientist. I work for this lovely company with the name Data Drivers, based in Hamburg, Germany. Yeah, we are a consultant, IT consultant company of 40 people based in a group, so-called Zunbert Group, with some other consultant companies. And we have like in total 400 people working in that group. And I want to take you to a little journey with PySpark today. And just to give you a short overview what you can expect. The first one is we will take a look at some base principles to revisit some things from scratch. Afterwards, we will go on to the machine learning capabilities of PySpark and get to know a business case example where we fit a simple model. And afterwards, we will move with that model and the business case to the cloud, namely AWS, to do like a real-world example, even though I mocked it for sure. And get to know like how powerful is the cluster at the end in the cloud, because at the beginning to like get started and to get to know the principles and so on, we will stick to our local laptop and simply be on the local host to get to know some syntax and basics and whatever. But I promise I will take a look at the time. If I get in time pressure, I will skip some details. We will definitely go to the cloud at the end. So you can fork the repo right over there. I've written down it. I realized that the QR code does not make really sense because mostly you are not working on your iPhone, mobile phone, whatever. And afterwards we hopefully have a better understanding like what this is and how we can get along with it. And having said that, let's get started. So there are several options I provided how you can follow. The option 0 is simply to lay back and let me do everything, and you can fork it and go through the details afterwards, so no need to live code with me at that point. If you want to, you can build a virtual environment and install like via pip or poetry or whatever your event, and then you can get started via Jupyter Lab. Also, I provided the Docker file, so you can build the Docker image and run it on the Docker if you don't like virtual environments for whatever reason, or you can go directly to Google Colab. These are the 3 notebooks we will take a look at, and these are the options you can follow.
Notebooks require access. The links.
Really?
Yeah, I clicked on 2 of them.
Can you make it public?
For sure.
But maybe I'm just having a bad day again.
Any one of you faces the same?
Yeah.
Okay. Okay. So, I'm sorry for that. All right. Number 1. Can you try it out for me?
Yeah, it works.
Okay, perfect. Perfect. Number 2.
So any of those links should be okay after you're done, right?
I don't know. I don't have that.
They are.
Because I don't know if I'm supposed to use all of them or only one of them.
Anyways. All right. Thanks for the hint. And let's get started with the first notebook. So I really want to start from scratch, and then we move on to the concept of data frames, and we will do like a hands-on example where we take a data frame and we'll do some transformation on it to get a specific result, and afterwards, yeah, I want to share some things what you can do, some pitfalls, some do's and don'ts, and yeah, this is just like how we get started. So we start at the local host, which means that, or maybe just to stop for the moment, who is aware of what is Spark? What is Spark's purpose? Okay, not everybody. Then I will go back to the slides for a moment and explain it. So Spark is an open source framework by Apache. It's now 8 years old or 9 years old. I guess it was first version was published in 2014, and it is a framework which one is able to do processing in parallel. So to execute code and transformations and whatever, also machine learning, but not only on your single computer, but on a cluster which one can scale up to however how big it should be. Because like yeah, you're limited to your own computer with your whatever 16 gigabyte RAM or 32 gigabyte RAM. And this may not be enough for big data, and yeah, with Spark you're able to parallelize big data, and yeah, this is what we want to take a look at. Spark has several APIs for Java, for Scala, and also for Python, which is PySpark, which I want to talk about. And this is what we move on to at the end. I want to go to the cloud, to AWS, and show the problem we got to know here on a bigger data set. And this should not run on the local host, but on the cluster we will define. We will define a cluster with several worker nodes. Hmm? No. I go back here to the notebook. So at the beginning, we simply mock like our cluster, which is not really a cluster then on the local host. But like yeah, to get a sense and to get to know the key concepts of it. So we have this so-called Spark session, which is more or less our Python entry point to then a cluster. And what we see here now is that the cluster itself is only built on localhost for the moment. But later on, we will see that it is a real cluster. You can also have access to your UI. I will come to it back later at one point. And this might not be possible if you're working in Colab, I don't know, to open the UI, but I will explain it later on a specific example. And yeah, so the Spark session is the Python entry point for your underlying cluster, your computation engine. And yeah, to start from scratch, the first data structure they introduced back in the days were the so-called RDDs, resilient distributed data sets. I painted like a little picture here so that one might imagine what's happening behind. So in my Python environment, I might have like a simple list of whatever. These are just some integers, but this can be data, this can be Python objects, this can be whatever. And yeah, what I do is when I create an RDD is this data is distributed then on a cluster. Imagine you have like a cluster of 3 different execution engines. Then you could set it that it's distributed like you see here. And typical for a simple list, it does not make any sense because it's super small. But one can define like what is at which amount of data it should be parallelized. And yeah, we can do it via the following. I simply have here a simple Python list with 1,000 random variables, and what I do is I simply parallelize them. And now, yeah, they are parallelized. We are on the local host, but they are in the structure of the so-called RDBs. And now we are able to get to know the first principles of Spark, which is namely the transformations, the so-called actions, and the behavior of lazy execution. Yeah. So transformations describe simply operations on your RDDs or later on data frames. You can simply imagine that as a simple Python function, map, lambda, x, whatever. And actions are operations which need really the result of a data frame. Like if I want to print it, write it, count it, or whatever, then I really need to have my result in my hand afterwards. And the thing is that as long as I don't call any action, transformations are not executed. And there's a specific reason, because what we will get to know later is the SQL engine that potentially transformations or a list of transformations can be optimized. Yesterday I heard a very good metaphor by Richie Wing, who's the creator of Polars, and he said, like, if I ask you to grab me a coffee and then you come back and then I ask you to grab me sugar as well, then you have to go again. So it would be better than if you have waited until the end and then to still go. And this is a nice metaphor for a lazy execution. And yeah, we can take a look here directly. For instance, one action is take. So I really want to take from the cluster what's lying there. Here I want to take the first entries. And yeah, we have now a simple list, but this could be Python objects or data or whatever. And then I really need to go to the cluster and yeah, query my data. One can see it very nicely if I do the following. I will now map a function on my RDD, and this function contains like taking a nap for 2 seconds, time sleep. And what I will do now is I will map this function to my RDD. So this function should be applied to every entry lying on the RDD, and we will see that it executes immediately. But I mean, it should take a nap. Why did this only took here a millisecond? And this is because of the laziness. I didn't ask for a result yet. I didn't ask for any action. So it recognizes like, okay, I should apply this function, but it was not forced to do it yet. So it waits until it has to. And this is when I click here, then this function will be executed, and also the first 5 results will be shown. And you see here now it takes time, and this is not to I/O reasons, but because of the time point sleep. Anyways, nowadays more or less nobody works with RDDs anymore, but we work with a more convenient layer, the so-called data frames. So this is built on RDDs, but it's a high-level API with working with structured data, like you would do in a database. So you can later on we will see perform SQL on it, or join, or do transformations and whatever. And the concept of this laziness and to collect all transformations and wait until the first action is called applies here too. There are several options how you can create a data frame. You can do it from scratch, directly via Python code in your Python environment, and then it will send it and parallelize it on your cluster. Or you can do it via an RDD, or you can read it from a data source. I can simply do it here from scratch. The same we already saw, a random example of 100 random integers. And I clicked here on show to get it here in Markdown. And what we can also see is here that every data frame is a schema, and the schema consists of which columns are in it, what is the data type, and am I able to put nulls in it or not? So is it nullable or not? I will skip this part from here, that one, to transform an RDD to a data frame, but go directly here to a data source. So in general or in practice, you won't read or you won't define data and then send it to a cluster, but you want your cluster, you want directly have access to your data source, whatever it is, a data lake or a database or whatever. And what I will show here is I simply read a simple CSV. So I create a data frame out of a CSV. Having said that, there are also some other possibilities, like you can read a Paquet columnar format as well, which we will see in a minute. And you can also connect really to databases via JDBC. This is also possible. So on the cluster, then the data is automatically pulled. Yes, what we will take a look here has a specific reason, because I'm a big football fan, and what I will do now in the hands-on example later on is we want to create a table out of football results. And there's a specific reason I didn't update the database. I will tell you later. But yeah, what you can see, like the syntax looks, I go to my Spark session, say read, and then I want here to read the CSV. It includes headers. We can take a look at how it looks like, and we will see here the first match day of the German Bundesliga, soccer in Germany. And we have our results. Munich won against Frankfurt, Augsburg lost against Freiburg, and so on and so on. So this is like the beginning of the season. And what we already can see here is that it's really bad at automatically schema detection when it comes to CSV, because it has no further information. So you see that everything is like in a string, is interpreted as a string. And that's not really the case, because like obviously both are integers. And so what I did in advance, I casted a little bit. You can see it here. I commented out because I simply took this data frame and casted some data frames, casted some integers, and then saved it as a Paquet, because Paquet, as we will see later in the cloud example as well, is more suitable for parallel processing. And also the Paquet format also stores some meta informations like mean, median, and so on. But what one can see is it's kind of strange syntax sometimes, and this is what I forgot to say yet, is that because Spark initially is built via Scala and Java and basically runs on the Java runtime, you will often see this camel case, which is not really Pythonic. And this is simply a thing we have to live with it, because it wrote historically, and we will see it on other examples later on as well. Sometimes you simply have to live with some maybe unintuitive syntax regarding pure Python, where one is more used to camel case, and not camel case, but to snake case. And especially if you cast here, you have to call the type and stuff like that. So these are some things you simply have to deal with it. what I do here is now I read this data frame again and take a look at it. Same, but in that case, I casted like here the integers, which is the goals for the home team and for the away team.
Excuse me. So when you imported your CSV file, why did you identify those master rows as numbers?
Because it's very bad in automatically schema detection. I think that Pandas is able to do it, like for a certain point, but yeah, here simple it's very bad. So in general, one has to strictly define schemas when you're using PySpark.
So if you have a lot of columns, would you just do manually?
Yeah, it depends. If you have like a CSV, then you are more or less forced to. But yeah, in general, you would better use a paquet or connect to a database, and there you have the information about the types. So,
is there a better, like, quicker way to read from CSV and infer and set up the types apart from transforming it to Parquet first and then? You
yeah.
always have to go through Parquet.
Yeah, you could read it from CSV and then cast everything.
Okay, yes, I know.
Yeah, this would be possible. So what I want to do is now I want to get basically the table out of the matches. So what we see, what we already saw is that we have here our data frame, which includes the matches. And what I want to achieve is I want to have at least a data frame, which is the current table. So how many points collected each team, so that I get a sense of who's first, second, and so on and so on. And with that goal, we do now a couple of transformations. And what we see here also is that it is executed immediately, and the reason is that we have this lazy transformation as well. So nothing happens until I call the next action. So it's just Spark realizing, okay, you want to have a new column, and in that column you have the kind of you have a data, and I do the next step, and so on and so on. And what you can also see here is what I already mentioned. This weird syntax at some point, because again we have here this camel case, or here we have like the whole column, which means that that this here is not a string, but it is technically the whole column. If you are familiar with polars, you might already saw that. Also, you might ask now, what the heck? Why do you do that? Why don't you just use SQL for the whole thing? And the reason is that I do it step by step, because like when I build software around it, I can later on test everything. And this is quite cool. I mean, I can define which points of that I want to wrap up in a function or whatever and test it. So I'm not forced to write a huge SQL, but I do it step by step. I can do it step by step, unless one can use SQL as well. We will see it. But it helps me like to build more stable software at the end, and to be able to test it. And also, what we will take a look at in a minute in the UI is that it is able to optimize everything. So to get the table, what I need to do is I need to collect the points. If like there's more goals for the home team, then 3 points for the home team. If not, 0 points. I do the same with the points for the guest. And then I also like have some renaming stuff, and also I need to make 2 data frames out of it, because at the end I want to union it again, because I want to treat the home game same as the away game, the away team. Then I will union it, and then I need to collect the sum of goals and the sum of points for each team. I will sort it because like the first place will be for the one with the most points, and the second criterion is the better goal difference, and then I add an ID for the place, and now we can take a look at it. We will take a look at the UI in a minute as well to see what's happening behind. But you can get a sense of why I didn't update it, because it's not up to date. It's 2 weeks ago, and basically I was born and raised in the near of Dortmund, so Dortmund is my home team, and we were in place 1 and we lost it, and there are just 2 matches to go. But it broke my heart to update the database. So this is the reason. I lived back in the days, 2 weeks, but there are still two matches to go. So yeah, we will see. You never know. Just to have a short view on the UI is very cool. You can take a look here. This is what I executed just some seconds ago. Basically, you can see here all the actions I took, I called, and this is like.
How did you open this?
Yeah, it is the link you get here, but I think it's not possible if you are in the Colab. I don't know. Have you tested it, anyone? Yeah.
It works.
It worked.
Okay.
Running locally, do I really need to use the Docker file and run the Docker container first and then?
Okay. Yeah. There are 3 options. You can run the Docker, or you can build a virtual environment, or you can do it directly in the Colab I provided.
No, it says 3 options.
And what we can see here is like execution plan. So Spark already realizes that later on I make like a union, and I don't want to dive too much into the detail, and honestly I'm not a data engineer, I'm a data scientist, so there is a specific point where I will also lose myself in this duck. But what it does is, if we recap, what we defined is we have a couple of transformations, and as I said that Spark is lazy. It collects all these transformations, and afterwards an optimizer, the so-called catalyst optimizer, analyzes the whole plan, everything what needs to be done, and then it tries to optimize it and to run it optimized. And this is what you can see here, because like he already recognizes later on I do a union, so I can scan the data twice at the same time. It helps me to be faster later. Yeah. You can do SQL. I provided some comments here. It is possible if you say like, this is like, I don't want to test it anyway, so this is like too complex for the moment, or I have like a bunch of things I want to do now. I can do SQL. I can simply register my status quo and then query my data. This is possible. What you can also do is you can create so-called user-defined functions. This is possible as well. So you can directly perform pure Python code on it, and you say like you go to the data to a specific row and do whatever you want to do. This is also possible. But if you do it, then this is a black box for this optimization, this optimizer. So if you have a UDF and then it's like, okay, this is pure Python. This is a black box for me. I can't optimize that. So you lose a little bit of efficiency if you perform a UDF. And especially when it comes to ETL transformation, if it's possible to solve it via SQL, functions and the built-in function from Spark directly, you should try it out because it makes everything faster. Before we move on to machine learning capabilities, there are some pitfalls, or especially one pitfall I want to share with you, and it's like the following. If you take a look at this code here, we have two actions. That one I want to count, and here I want to print my result. I want to show. These are two actions, and what will happen now is the following. If this code is executed, Spark realizes, okay, I need to read the data, then I do some transformation, and then here's the first action. The first action will be called, which means that these two transformations, or this transformation and this reading process will take place. So far, so good. Now I go on, I do with my resulting n, whatever, I'm here in my Python environment, and I'm like, okay, when it's not many matches there, I want to print it's too early, or if not, I want to go on. I go on in both ways, but I want simply to have a little message. And then I have further transformations, like I want to calculate here like a simple result column where I can see if it's a home win or away win, whatever. And I have a second action. And the thing is now that when I call this action here, the whole plan is executed. Even this one, but this was already executed. So it happens twice, and this is definitely inefficient. And the reason for that is, again, laziness. So the whole execution plan is saved, and here I will do everything again. So this was already taking place, but it's not cached automatically. And what you can do is to persist. That means that it's more or less cached. It tries to cache it in the memory, and if there's not enough place here, it will persist simply on the disk. And in that case, here you have the first action. This is calculated. Here you have the second action. This is calculated based on what is cached here. And this can be very painful if you have like a huge ETL pipeline which you forgot anywhere to persist, or call an action twice or whatever, because you might end up with your whole pipeline executed twice. So this is definitely one of the pitfalls.
Does it matter if I persist before count or after count?
Yeah, it does matter because it does matter because persist is not an action itself.
It's not.
Yeah, no, it's not an action itself. Count is the action, but persist is not. Which means that if you persist afterwards, it will go the whole way again. It will execute everything. And then it will persist here at that case, and later on it will just go back until here. But you persisted after the action, and this does not happen in that case.
So what you're saying is that the action of persistence happens because we arrive at count.
Yes, correct. So, which means that persisting itself is not an action. It's just like what you say Spark should do, but it does it in that moment. It is not.
What if you put in like different cells? Will that still be the same in terms of like the execution?
Yeah, for sure. Because like here I'm in my notebook, and I promised that we will go on to the cloud. I mean, in general, you won't have a production system, not a notebook, but you will have a Python script and software built around it. And but it does not make any difference whether I'm here in my notebook and have different cells or have a whole script. I will skip the other pitfalls here. You can simply take a look at it afterwards. It's like there are some things with case sensitivity and potential duplicated names or errors which will you see in the moment you call the first action and not immediately, which might be an issue. But yeah. I want to move on to machine learning to get to know a business example, and with that business example, I want to move to the cloud then. So to wrap it up, for the moment, we have our Spark environment simulated locally. Yeah, we got to know our RDDs, we got to know data frames as high-level API, which is like more or less the standard. We got to know the schema, and what's the most important thing is we understood, hopefully, the concept of transformations, actions, and this lazy execution. All right. Yeah, the second notebook. This will be a little bit faster, which gives us time later on to move to the cloud. For the moment, it will take place at localhost as well, because we focus on syntax and what's happening. But yeah, we will go to AWS with that one. So I prepared a data set. And what you can do with PySpark is, of course, you can perform some EDA. I would not recommend it to do it on a full-scale dataset, because, as I said, that you have these issues of maybe executing the whole pipeline plan twice or 3 times or whatever. If you call actions, and if you do an EDA, you want to take a look at the data, and show print is always an action. But you can do it for the moment. There are some possibilities, like to take a look at it. But the way here, okay. This was the topic we had like at the beginning, right? So it forgot it, honestly, that you can call the infer schema. Then Spark tries to infer the schema. Let's see what we have here. Postal code. Okay. Yeah. Okay. Interesting. Forget about that. Sorry. It is possible to infer the schema via CSV directly, but the thing is, it's not sure whether you want it or not, because yeah, we have here, for instance, like we will see later, a postal code, and it depends, like if you want to handle it as an integer or a string, if you want to do some joining and whatever. But let's take a look at the data frame. That's not really cool. It's too big. It is this typical Markdown output. What you can do as well is you can say here vertical, then you get like the first two records, which is a little bit easier, but also there's this option to make it look like basically a pandas data frame if you want so. So this might be a little bit cooler to take a look at it. You have your customer ID, specific postal codes, some numeric features. I simply mocked it, and then we have like something here where this customer lives in a countryside or intermediate area or in the city. As you see, I already coded it because yeah, I did some pre-processing. Because what we want to do, we want to catch up this target variable 0, 1, and in our case, one can imagine that this is maybe a churn example. So you want to predict whether or not a customer is likely to churn. This is basically one of the business cases I face very often. Like if you want to understand how likely is that a customer churns in the future, and based on that you can like make some decisions out of it. And that example exactly we will go to the cloud later on. Yeah, okay. One can do also like here, calculate the mean. Again, this is not very nice. This Markdown output, but we can use that one. So one get a sense of like what is the mean, what is the standard deviation, whatever. And yeah, let's build a model out of it. So I want to take my features and I want to build a model which is able to predict the target variable. And Yeah, this might look a little bit like scikit-learn, but there are some differences. This is one of the takeaways I want you to collect today. We already know data frames. We already know data frames. We already know this concept of lazy execution. And what we get to know here are now 3 new things. The first one are so-called transformers, which are objects which are able to take one data frame as an input and transform it, whatever. And the output is again a data frame. Then we have estimators. Estimators more or less will be, in our case, machine learning estimators, which take a data frame and fit something, which is able later on to be applied on the data frame. And also we have the concept of pipelines, depends on the time, if we take a look at that as well, where one can chain everything together, which makes it easier to handle, because like you have one Python object, the same as you have in scikit-learn, maybe. Some of you are aware of that one, scikit-learn pipelines, this is the same concept. Yes. What we have to do here, we have to apply the so-called vector assembler, which means that out of the feature columns for the machine learning model, there will be created a so-called feature vector. And we can see it here, not really because it's here cut off, but I can take a look at it here more deeply. So what happens is that it takes all the features for every entry in the data and builds so-called dense vector out of it, which makes it easier to train the model in parallel later. So this is like a typical pre-processing step you have to do at the beginning. Then, as everyone, whoever did some first steps with machine learning is aware of, I need to train test, split my data. Here I train test 80% train data, 20% test data. And all right, then here we can go. I simply choose the simple model, logistic regression. And I define like what is the target variable, what is my feature column. This is the feature vector we just created. And here is the main difference between scikit-learn, if you are familiar with it, and Spark machine learning library. Because in scikit-learn you would simply call now logistic regression .fit, and you don't get a result. So the object itself is able then to predict again. Here you get a specific object back, and this is the concept of the transformers, what we already saw on the top. So the logistic regression is an estimator. It is able to estimate some hyperparameters, and it gives us back a transformer. So it's not possible directly to apply this estimator to a data frame, but you need this transformer, which is the return.
Is it the same as like predict method?
Which one?
Like transform here is the same as predict?
Yeah, you can say like it's the same like predict, but in scikit-learn you would have something like LR point predict, and here you get back the model, and this is you need to take this model, which is a transformer, to apply.
I hope it's the same, but maybe it's
No, in scikit-learn you would skip that one. You would directly use this object. By the way, I have the time. I provided some comparisons here in the sandbox. So if you are interested afterwards, you can simply take a look. I have some simple ML natively via scikit-learn and Python, and a comparison of how this would look like in Spark. And also the business case we will take a look at now. Is also compared here directly via PyFiles. So if you want to take a look at that later, you are welcome. Yeah, so what do? I fit this model here and I do my predictions. Yeah, regarding parallelization, because like yeah, we know that in real world, we would go to a cluster where everything is done in parallel. How this exactly works is highly dependent on the model itself. So, for instance, an XGBoost is not that easy, cannot easily be parallelized just to a certain point, whereas for some things like KNN clustering, you can parallelize it easier. For those of you who are very interested, there are so many research on about like how to be able to parallelize machine learning models. Yeah, good luck with all the papers out there. But yeah, it is so everything which is built in the machine learning library of Spark, you can be very sure that will be parallelized as far as it is possible. So we have our predictions containing like the prediction and also a probability, which might be the equivalent of pred-proba in scikit-learn. One can also like test how good this.
Excuse me. If you want to change the cut probability and predict just based on whichever is larger probability, can you change? Is there a way to do that, or how can you get the probability of, let's say, class 1, and then you can of course use any threshold of color which you want. Because the last column is based on whichever probability.
Yeah, good call. Honestly, this is definitely something I have to look up again. I struggle with that in scikit-learn all the time because I feel like when I do binary classification, what exactly is the order?
0, 1 in scikit-learn is just like with the square brackets, colon, comma.
Yeah, and in scikit-learn you also can you can call like the classifier and say like target values, and then you have the correct order. And honestly, I have to look it up for Spark. Yeah, good point. Good point. But here, what we see is the probability for 1. But yeah, good question. I'm not able to answer it. I will look it up and add it to the repo afterwards. Yeah, another thing is like where you can see that Spark historically wrote is that you are not able to perform accuracy and F1 score and area under the curve at the same time, because there are different evaluator classes for that. This is, sometimes you find some weird things with PySpark. So for those of you who are not familiar with machine learning so far, this accuracy is relatively simply metric, like what is the percentage of the true value I predicted correctly. F1 score is like a harmonic mean between some other matrices called recall and precision, and area under the curve is also another metric. Would take too much time, and it's not the focus here, but there are simply different metrics where I can get a sense of how good my model is. So I can see it here. I have area under the curve 0.84. Okay, so far so good. Not that bad, but always depends on the baseline. But yeah. For sure, if I once have my model in my hand, I want to persist it so that I can load it in another environment. I don't want to train it every time before I want to use it. This is possible here simply via calling model point save. And what we will see here is that it will be saved directly. It takes 2 seconds or so till I can see it here. Here it is. My model is saved with some specific metadata and some parameter stuff, and this is also saved in a Parquet file. So not like scikit-learn where you would use Pickle to serialize your model, but here you have this Parquet setup. And now you can load it, right? So I mean, we use PySpark here, but you can also use it in an environment where you have Scala or Java directly. So yeah, it's not pickled. It is written down as a package file, so it's language agnostic at that point. Yeah, and you can also load it for sure. The interesting thing is again that here are some different objects. The logistic regression was the class for the model itself, and now we have this logistic regression model, which is able to load. And this load method is not implemented here. I assume that this is part of that one, but it's not. Yeah. So again, some typical things which you might find at the beginning a very intuitive or whatever, but one gets along with it after a time. And yeah, we still have some time, so we can take a look also on pipelines. As I said, it is also possible to chain different steps of your process in the pipeline. Here we have this vector assembling, this transformation, and the logistic regression itself. We can store it in the pipeline. In a real world, it would be a little bit more complex because you don't only have like this vector assembling. You might possibly have whatever a standard scaling of a model because like the model has some assumptions you need to make sure which are fulfilled, or you have to one-hot encode something, categorical variable or whatever. So everything would be able to be stored in a pipeline. And yeah, one can do the same for a pipeline. The concept is exactly the same. You can fit it and you get back to the transformer. And with the transformer, you can make your predictions. Yeah. I will skip this part because maybe it dives a little bit too into details, but just a note. For those of you who already built some machine learning solutions, you might be well aware that different parameter setups of the same model lead to different results. So it might be a good idea also to perform some optimization on the model, hyperparameter stuff, etc., etc. I will skip it for the moment. You can take your time afterwards, check out the repo. I hopefully provided some comments, etc. Yeah. Yeah, and as I already said, that the real world would look like a little bit more difficult because machine learning is not that easy as I did it here, but we have everything in our toolbox so that we can handle it. So we are almost ready to go to the cloud, and just to do a little wrap up. So we don't only have Spark SQL engine, which makes it possible to do ETL, but also we have machine learning capabilities on our hand, so that we can train and do inference. We have seen inference, but we will see it later on in a distributed way. And the syntax is very similar to scikit-learn, but there are some differences definitely. We got to know the concept of transformers and estimators. Yeah, the fitting process is parallelized. On which degree it depends highly on the model architecture, and yeah, the resulting model can be loaded and loaded again in a completely different production environment.
What about flexibility of like parameters compared to scalars?
What exactly?
Like you can choose provide so many different parameters.
Hyperparameters. I would say it's basically more or less equivalent. Like, for instance, for a random forest, you can choose max depth, how many estimators, what else? The minimum sample leaf size.
Like for
Whatever.
logistic, let's say, regularization. Like
Yeah,
one,
yeah, yeah.
two.
So this is not optimized in the sense of machine learning, but yeah, you can also like add regularization parameter, do your lasso regression, whatever you want to do. So you have more or less the same amount of freedom than you have in a scikit-learn setup, but you can do it on a cluster with millions or trillions of data, and you're not only here on your local laptop. Yeah. What I want to motivate before we move now to the cloud, I won't do again everything in a notebook, but I will do the following. So we will move to AWS cloud in a minute to see a real cluster in action, and we will load 3 data sets. The first one is master data set of customers. Imagine like in the real world you have different data sources, and say here we have data with customer master date, which only consists of the ID, customer ID, and the postal code. And the postal code later we need to use to join the region we already saw, and via the customer ID we can join some usage features, some already standardized usage features. This is what will happen, and then we need to do some other things. We need to pre-process everything, so the purpose is that everything looks like it did here. So I want to have a data set in my hand which looks like that one, such that I can apply a pre-trained model. And for this, I need to do some steps. I need to take this data. I need to pre-process it. Pre-processing in the sense of join everything correctly, and also one hot encode. I will show it in the script later on, which we will send to the AWS cluster where this takes place. Then we want to load, apply a model. So in that case, I trained the random forest classification model, which is also a classifier, and I want to apply it. I want to apply it to get a sense of what is the probability here, and because like the probability comes within a vector for all options, I pre-process that you really have a float here in our hand, and then to build a bridge to a real-world scenario. What you would do now would be kind of applying a business strategy. So if I know that a customer is very likely to churn, I might be willing to give him like a very big incentive, because like losing a customer is always very expensive, because you have to calculate what it costs you to gain the customer again. And so churn is a big thing, and what I want to simulate here is simply some business logic, and based on the probability, the churn probability, which the model gives me, I would simply want to define which is the incentive, and I have a fallback and some whatever version 1, 2, 3, 4, 5. And now you can imagine at the end of this process, there might be a business department, and they take the result and say, okay, the version number 2 is like 100 euro discount. Version 3 is 150 euro discount, whatever. So this is the business case I want to show. And yeah, now it's time to move to the cloud, namely to AWS, to do this not here on my local machine, but to do it in a real cluster and to get a sense of how this looks like in production. The data itself, it lies in a so-called S3 bucket, which is basically the data lake in AWS.
excuse me, is there code on your GitHub?
Yes, there's code. We will see it here in the script, and also I shared the code. And also I divided the code to one as a template, what you need to do to go to AWS Glue, because you need to wrap up some things. And then I copied everything we saw in the notebook inside that. So I will show it in a minute, but let's come to the business case. Why isn't it? Okay. I provided the data here. We have our demographics, simply Parquet file. Demographics only consists of the postal codes and what country those people live in. And for the customers, I marked data which is a little bit more. You see, it's not that really big, but I simply randomized some customers, so that at the end we should have here something like 10 million customers or whatever, just to get a sense of it would be in real life scenarios a little bit bigger. So this is my data, which lies in S3, and also in my data lake in the cloud, I have the model. We already saw how the model is persisted. And what I want to do now is I want to run everything, and the centerpiece, we see it here. So I will read my data from the data lake in the cloud, the customer data, the usage, and the demographic data. I will load my model, and then I will preprocess, which means joining and one-hot encoding and stuff like that. I will apply my model, I will apply my business logic, and the end result should be written down back to F3 again. This is what we see here in this nice architecture picture. It's not the most complicated architecture of the world, but yeah, for those of you who already have been to the cloud, you might be familiar with these pictures. This is more or less the script. If we have some time later on, we can dive into the details, but whatever might not be that interesting at the moment. What is cool is here is that I can choose how my cluster should look like. So if we recap that, what we will do is basically not on my local host, but on a cluster which looks like that. I want to spawn some workers which will do the work afterwards, and I can do it here. I can say like, what is your Spark version? How each worker should, how powerful each worker should be. I simply take the standard one, which is 16 gig of RAM, and I request here simply 3 workers. But I could request 1,000, and I could request 1,000 of workers of 128 gigs RAM, and then I have like what is it? 10 terabyte of RAM. So I can scale it up if I want to. And the cool thing is that with AWS Glue 3, you also are able to select the automatic scaling, which makes it possible for the cluster automatically to realize I'm running out of memory or things take some time. I scale it up. I scale the cluster up automatically.
One question
Yes.
might be very naive. So this whole thing, how does it scale in terms of payments? I mean, so this is not something that we can try out at home, right?
In that case, not directly, because you need an AWS account for that.
Yeah.
It costs a little bit, but I mean, it's just 3 workers and a small amount, so I ended up with $1 this month.
Okay.
For my sandboxing in that case. And yeah, I want to show what happens. I can simply click on run, and then it will run, and it will take like 2 minutes or so for these 10 million examples I have here, and most of the time will be like to spawn the cluster and to stop it. So it's serverless, which means that if everything is done, everything will be shut down. But you see that I already tested it just before the workshop, and we can take a look at some details here, for instance. And because of the fact that it just took 2 minutes, it's not that interesting, but I have a snapshot of a cluster of one of our clients. So what we can see here is it just logs every minute, and it only takes 2 minutes. So it's not that real insightful here. But what we can see is the memory usage of the clusters. So we can see here simply it logged 2 times, and we see that more or less the driver has nothing to do. And there are 2 executors where magic takes place, and the first executor has like memory usage of 11%, and the second one 6%. So I tried to build a stronger example, but it's very hard to mock a data set, which is basically then that big that a real world cluster would be really occupied for a couple of minutes. But like to end up with a snapshot I made from one of our customers, how this would look like in reality is here we have AWS Glue in action on the real world data set of one of our clients. This is basically a batch process taking place. You see it. It's 5 o'clock in the morning, so it's very early, and we speak here about 30 workers, and each worker has some memory, has 30 gigabyte RAM, which sums up to 1 terabyte RAM. And you can see here that it takes some time, and also it has some peaks and so on and so on. And with that one you can have a sense of like what is the basic workload in your cluster, and at which time happens what and whatever. And also you can take a look at the logs, and as I explained, that sometimes you find yourself with it never ends. Maybe I made a mistake, maybe I missed something regarding the lazy execution or whatever. It's always good to take a look at this dashboard. Honestly, I don't know what is the equivalent in Azure and GCP, but there are capabilities there as well, where you can spawn a cluster and get your Spark code running. And we can take a look at the result. What should now be ready here. So take a look at Glue and our run. I just started here a couple of minutes ago. It ended. It took 3 minutes, and what it did is it should have written down all the results here in the output folder, which is true. 12 o'clock UTC time, so it fits. And here we have like the result. And imagine now that this example is very, very big, so that I'm not able to run it anymore on my MacBook. But we talk about many gigabytes or terabytes of data. This is a cool possibility to move to the cloud and to use virtual machines. And PySpark is very, very cool and powerful tool for that. And
can you just open one file? Can you show what's in one of these files?
It's a Parquet format, so it's simply if you take a look at the script, we can do that. If we take a look at the script, we will get a sense of what's there. It's simply the customer ID, the probability, and the incentive. So the result of my applied business logic. And because it's not a CSV, it's a Parquet, I can't take a look at it immediately in the UI. There are some possibilities in AWS. You can query also direct to your data lake, but honestly, I didn't do that for a long time. So I'm a little bit scared to do that live now. I would propose that we use the remaining time for some questions or feedback or whatever. Yeah, I provided a lot of code here. You can go through the notebooks again if this was interesting for you with more explanation. I added comments, as I said. I also added some comparisons here, like how things look like in a native setup and how things look like in a Spark setup, so that one gets a sense of yeah, what are the differences and what are similarities. Also, I provided a little template so that one gets a sense of what do I have to do to get Glue running, and this is like the final script I provided for AWS Glue. Not that anybody is scared to take a look here directly. This is more or less everything we learned in the notebooks combined with what I have to do to get Glue running. And you can take a look at that. You can contact me afterwards if anyone has specific questions afterwards, or you can ask me them now. So yeah, thanks a lot for attending, and just to use the time for some shameless marketing. So if anyone of you thinks about moving to Germany, or we are thinking about like our clients are more and more open also, and not everything hasn't taken place. So our amount of remote work grows. If anyone wants to join us, we are always looking for talents, data engineers, data scientists, DevOps engineers, software engineers. Very nice company. I now work there for 3.5 years. It's a lot of fun. Leave me